So it was hastily established to train teachers. Train teachers rebuild France's collapsed education system. It hosted lectures by, you guessed it, some of the names we mentioned earlier. Monge, Lagrange, Laplace, Legendre. It was short-lived in its original form, but it became a precedent for state-supported mathematical instruction. Lecture notes from the school, especially Lagrange's and Monge's, and it influenced pedagogy for decades to come. And just two more we'll mention here before moving on to the next section. This is taking up a lot of time. Okay. Also founded in 1794. The École Polytechnique, the crown jewel of revolutionary mathematical education, founded with strong input from Monge, Carnot, and others to train engineers, artillerymen, and state scientists. Monge served as both administrator and lead instructor of this thing, shaping geometry and analysis curriculum. Students were taught descriptive geometry, analytic geometry in 3 dimensions, mechanics, applied calculus. And it became the prototype of modern scientific military academy. Its influence spread across Europe and America. Educational diffusion, this is more the reform part. Educational diffusion and textbook revolution. École Polytechnique curriculum spawned a wave of analytic geometry textbooks. Authors included Biot, Lacroix, Poussin, Lefranc, all building on Monge's lectures. The term analytic geometry came into popular use through these texts. Mathematics became more structured, hierarchical, teachable at scale. We saw that with Euler, but now it's applied institutionally. A legacy still felt today. Coffee is so good. Okay. Let's look at some of the domains and their developments. So, these words get thrown around a lot, and these words are descriptive and analytic geometry. Monge's geometry descriptive, it introduced the method of double orthogonal or orthographic projection. It was used for military design and engineering. Things that really come into play when you're trying to rule the world. Like Napoleon pretty much was in Europe. Well, he just wanted to rule Europe. That's for them. He might have liked Australia-ish. Okay. Now, Monge's lectures at the École Polytechnique, they formalized solid analytic geometry and differential geometry as well. Analytic geometry in 3 dimensions, as I keep mentioning here, became central: coordinates, tangent planes, intersection curves, and transformation of axes. There's a plethora of things named after Monge here, not the least of which is the point, Monge point, and circle. And director sphere emerged from his work in tetrahedral geometry. Textbooks proliferated, pushing solid geometry into the mathematical mainstream for the first time since antiquity. We saw it way back there with the Greeks, but I would argue that it's not really so much as like it's even more prevalent, because we go back to these big geniuses back in ancient Greek times, and it's really just a bunch of aristocrats decided, like, this is interesting, let's kind of, not to be too blunt about it, but who's going to be able to afford doing that stuff way back when? We've talked about this before, but it's going to be the people that are, like, extraordinarily wealthy in this time that people are rowing giant boats and killing each other with swords. So now we are more sophisticated. We kill each other with bayonets and muskets and cannons. So calculus in this time period. Calculus of variations. Lagrange pioneered this subject. I mentioned that earlier. Formalizing it with his method of undetermined multipliers and notation of variation. This example with these soap bubbles that comes to mind. Just I was thinking about that. We're not going to go into that because that's not what we're going over, but okay. And this is just to sort of speak to Euler being just the humble sort of guy he was. Euler delayed his own publication to allow Lagrange full credit for his general techniques. But Euler knew what was going on. Variational problems such as Brackenstones, brachistochrons, not stones. Histochrones, geodesics, and isoparametric curves. These became central examples in analysis. The subject deepened the relationship between geometry, mechanics, and optimization, which foreshadows what will come later in functional analysis. Which is it's a really good thing to know. Like, it's kind of like, we'll get into this later, but the way that the Bourbakis taught things was like, the Bourbaki group taught things, we'll get into the Bourbaki group later, they also come from France, but not this time period. Just suffice to say for now, they were a very important group of mathematicians, and what they did is they tried to put everything together in one cohesive, I guess, not exactly a narrative form, but a system of thought that emphasized rigor from axioms onward. And so, looking at it from this perspective, a good thing that would be, a good thing pedagogically speaking, is like in the same way that students transfer from learning calculus to later learning real analysis, you could put them on the track of learning calculus and variations before going into looking at functional analysis. But I don't know. I couldn't say for certain. Not yet, anyway. I can't say for certain yet. I'll get a better idea once I go and I look at it more properly. It's just something that occurred to me off the fly. So, speaking of which, foundations of analysis. So, Lagrange attempted to found calculus purely on algebraic expansions, leading to the theory of derived functions. Which is important because that's the way we do things. We do a lot of things coded in algebraic notation. And a lot of people have problems with that, but I'm just saying, look, if you were going to make it, would you have made it any differently? And they would say yes, but they would probably say yes, but let's put that aside. Algebraic expansions leading to the theory of derived functions. So here, D'Alembert and Carnot both pursued alternative metaphysical foundations for calculus. It was like limits and compensation of errors, respectively, you know. So it's like it's really only two that you can use. From this perspective, which are limits and also compensation of errors. You can tell which one we use more. At least at the rudimentary level. So, Cauchy established the formal limit definition of continuity, derivative, and convergence. This giving rise to modern analysis. The limit displaced the infinitesimal as the foundation of rigor. These developments marked the dawn of arithmetization of analysis. Function theory. So to deal with function theory in this time period is the following. Lagrange's theory des fonctions analytiques sought to eliminate infinitesimals by defining derivatives via series. Very hostile towards infinitesimals. What did the infinitesimals ever do to these guys, right? Infinitesimals via definition of derivatives via series. So Fourier expanded the concept of function beyond differentiability with trigonometric series, enabling arbitrary periodic representation. Expanded. Dirichlet later defined functions as arbitrary correspondences between variables, vastly expanding the analytic landscape. Cauchy developed theory of complex functions. And introduced key theorems of analytic continuation and contour integration. So, as you can see, there's a lot of stuff going on in this period. And so, it's kind of like hard to cover things in depth. It gets harder and harder to cover things more in depth the closer and closer you get to our current day. And the reason why is because, well, one of the things is like that skyrocketing deal I mentioned earlier due to this, it's just a logistical thing. You put all of these together, you institutionalize all of these things, and you industrialize in a way the theory, the means of developing mathematical theory. And of course you're going to get a radical change in output. As radical as the French Revolution itself was, right? So it's which is kind of in a way a tragedy to the case because you want to cover everything, but it's just there's only so much you can cover. So you can look at things via with formal sciences. You can look at things on the axis of its history as well as its theory from logic upwards, which we'll look at that. But for now, let's just go on to this next part, which is probability and statistics. So Laplace systematized probability theory in his Theorie analytique des probabilités and introduced the Laplace transform. Condorcet, applied probability to voting and decision making. Which, is kind of what we do for AI and a lot of the machine learning stuff. Which lays the groundwork for, as I should mention, social choice theory. Legendre introduced the method of least squares. Laplace later formalized its probabilistic foundations. Poisson developed discrete, so there's continuous, and discrete distributions. Which, of course, included his very own Poisson distribution and extended probability to judicial applications. Which, is kind of like, you see the Napoleonic Code, as juxtaposed to English common law. There's a lot more exactness within the French legal system that our legal system does not have, which is just an interesting perspective on how laws and whatnot are formed. You could get into a dialogue on whether or not that's because one system is predominantly Catholic and the other system is predominantly pluralistically Protestant, but that's a discussion for a different thing. So, probability and statistics here. And differential diffie Qs, man. Always thought that was such a weird way to call differential equations, but I guess it makes sense. Diffie Qs and mechanics. Not on cars, those haven't been invented yet. No, physical mechanics. D'Alembert derived and solved wave equations. If you ever take a course on PDEs, his name will pop up a lot. Onge and Lagrange applied differential equations to motion and surfaces. Now those things are common. Those things are common enough. Don't need to make a big deal over it. Okay, Laplace's operator and potential, this is a big deal, which is Laplace's operator and potential theory. Became foundational in celestial mechanics acoustics. Just gotta feel the music, man. No, but acoustics and gravitation. Gravity. There we go. Gravitation. So that's a big deal. If you could do that, you'd probably do it too. If you could influence all of these things. Doctors say it. Cauchy introduced methods for solving both ordinary and partial differential equations, including convergence guarantees. Which is just, it's insane. That's insane. How did you do that? Guarantees. ODEs and PDs. So Lagrange's variation of parameters, Cauchy's Bajorans and Kowalewski, Madagascar 3 all over again. Kowalewski theorem, advanced existence theory, which is just a wild name for a thing, right? But whether or not a thing exists, insofar as you can properly construe it. That's pretty well it for this development here on diffuse mechanics. We still have to get through Guass. And it's been like 2 hours. Okay. Number theory in algebra. If I skip a few letters here and there, that's fine. As long as I can just get it enough in there. Okay. So Legendre authored the first major treatise on number theory, and he proved special cases of Fermat's last theorem, which is going to be a big deal. Fermat's last theorem, I mean to say. For hundreds of years, until Wiles, who we'll discuss later, was able to prove it. But just being able to prove special cases, I think. I mean, like, it's, like, what are we talking about here? Like a really, really special case, or just a special case, you know? Because if you can get it, yeah, special case, it's impressive. Lagrange proved the 4-square theorem. Which is not the game, by the way. It's just, you know, that. And early results on congruences laid the groundwork for group theory. And then there's this law of quadratic reciprocity, which we'll see in an undergraduate number 3 course. Rediscovered by Legendre, became central to modular arithmetic. Su developed elimination theory. Which, by the way, elimination theory in a political context sounds a lot worse than elimination theory in a mathematical context. And algebraic methods. For determinant theory. You know, it's like it's an interesting way that the language sort of develops. Like a lot of the things that we kind of just take for granted for today, like determinants. It's like these were kind of like in the realm of, we call this thing theory, and then we expound upon it as a major branch, and then, you know, then it just becomes so commonplace that, like function theory, it's like, what? You know, it's like, oh, we'll just talk about functions the way that they are, because it's just so commonplace now. Probably no complaints from me there. That's kind of what happens to set theory anyway. So let's move on to the problems and solutions. Problem 1. What is a rational definition of length? It's rational, it's reasonable. By the way, anybody who says, something reasonable in an argument, it's kind of like, well, then why don't you just reason to me? Oh. So, what is a rational definition of length? Well, apparently it's this weird sort of like 1 over 10 million deal. 1 over 10 millionth distance from the equator. To the pole. Come on. Along a meridian. Now this decision prioritized Earth-based measurement over our oscillatory definitions, enabling international standardization. So this became commonplace, the metric system, right? So, very big deal. 2. Can arbitrary functions, right, be expressed as trigonomic series? To write where that's from, right? You all pretty much already know, but this is 1790 to 1799. This is Fourier. 1822. So can arbitrary functions be expressed as trig series? Well, the answer is yes. Fourier proposed that any function f of x defined on an interval could be written as a sum of sines and cosines. The Fourier series f of x is equal to a naught over 2 plus the summation from n equals 1 to infinity of a n times cosine nx plus b sub n sine nx. Coefficients derived by integrals over the interval, valid even for piecewise and non-differentiable functions. This introduced ideas of convergence, pointwise behavior, and functional generality, led to the creation of functional analysis, very important, and redefinition of what a function even is. So, well done. If you could answer that question, Fourier did, as he did, could be remembered to this very day. Okay. Now, on to the next one. Problem 3. How can constraints be enforced by law? No, be enforced in optimization. Yeah, this is some pretty cool stuff that you'll get to look at, I think, if you look at mathematical modeling of things. Because like that's all about, you know, well, a lot of it's about optimization. Because you can't account for everything. So the best you can do is like take fundamental variables of things, the least amount of fundamental variables, and model a thing. But anyways, so given a function f of x, y, z with constraints g of x, y, z equal to 0, Lagrange introduced a system of augmented equations such that he used this weird L symbol, which nobody likes now. This L, x, y, z, lambda is equal to f of x, y, z plus lambda g of x, y, z. Now, you'd solve for this equal to 0 to find critical points satisfying the constraint. So, how do I say this? It's kind of like looking for fixed points. We'll get into fixed points and stuff like that later on, which deals with mathematical modeling a lot more qualitatively with point array. But for now, it's just suffice to say that, you know, you look at things with this in mind here. Gradient, yeah. Right. Okay. This method remains a cornerstone in modern optimization economics physics. So you'll see this thing everywhere. Problem 4. Are all polynomials created equal? Are all of them solvable in closed form solution? I should say, you know, solvable via closed form solution, because solvable is it's a complicated thing. Because it's like, yes, you can get approximations for things, but does that make it solvable? It's like, not necessarily, but you know, if you define it to be closed form solutions, then it's like, well, yeah, absolutely. But are all polynomial equations solvable? No. Reason being, there's this big sci-fi series which I was informed of whenever I was at a chess club meeting a while ago, called like the three-body problem. And the reason why, you know, that was such a big deal, which we'll get into later, Newton wasn't able to solve this three-body problem because he was approaching it as though it required a closed-form solution. But the thing about it is it kind of, it's around the quintic, and you can't, there's no closed-form solution for the quintic. It's just too random, right? It's just too, what is it? Rather, what do I mean by random? What do I mean by, and it's too chaotic. What do I mean by chaotic? Well, the sensitivity of the initial conditions, sensitivity in regard to initial conditions of a thing. So it's like, you're looking at, say you're looking at a pool table, right? And you're playing pool, and you hit a ball, and then like all of the balls scatter across. Well, it's like that times like 1,000. It's very sensitive. It's like, you know, the butterfly effect. If you've ever heard of the butterfly effect, it's like, you know, a butterfly flaps its wings and then you follow the chain of events, and all of a sudden there's a tornado, and Kansas and Dorothy gets transported to the land of Oz. You know, it's like not that extreme, but you know, you can sort of get at what I'm saying whenever I say the sensitivity of initial conditions make the thing such that there is no closed form solution for it. But there's a different line of argument that's more precise that is dealt with in this time period. Lagrange studied permutations of roots and resolvents to access solvability. He discovered that general equations of degree greater than 4 cannot be solved by radicals. Only traditionalists. No. But it cannot be solved by radicals. And this led to the development of group theory and Galois theory in the 19th century. Conjectured what Abel and Galois would later prove: the quintic is generally unsolvable. You can have like approximations and these nice little things, but the quintic, no go. Yeah, and you can look at it qualitatively, which is what we'll look at Poincaré doing later with his topology. Poincaré. Okay. Problem 5. How can algebraic curves be eliminated? So this is owed to Bezout. (1779). Bezout devised systematic use of determinants to eliminate variables from systems of polynomial equations. He developed the Bezoutian matrix and established his theorem, which is two algebraic curves of degrees m and n intersect in m and points in general. This created a foundation for algebraic geometry and projective elimination theory. Yes, it's linear system of equations. It's like directly, yeah. So, okay. It's a lot to get a handle on, but it's fine. I think they can, yeah. There we go. Problem 6, can differentials be defined? No, they can never be defined. Without infinitesimals. D'Alembert and Cauchy. So this is a So the answer is yes. How did the two approaches here differ? Well, D'Alembert, he says, look, we can define derivatives via limits of finite difference quotients. Now, That's fine. That's nice, that's dandy, but it's not quite as formal, it's not quite as rigorous, it's not quite as specific as what Cauchy would later say. Not say exactly, but say implied, as in writing, that a derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Let's replace intuitive infinitesimals with rigorously defined limits. Set the standard for 19th century analysis and future calculus instruction. Which, by the way, like, we're not going to really get into this, but there was this popular movement later on to sort of try and bring back the infinitesimals and see how everything falls into place if you include them in non-standard analysis. But it sort of fell off, and the reason why, I think, is because there's probably some form of correspondence in between what you can do with an infinitesimal and what you can't do with an infinitesimal. And it's probably like for every thing you can do with an infinitesimal thing, we've already expanded dozens upon dozens of pages on the way that you can do it if you don't include infinitesimals. That's probably what I'm getting, but I'll need to look into that further. So. What is the probability of rare events? Poisson studied discrete random events with low probability and high frequency of trials. He found the limiting case of binomial distribution, which is pi k semicolon. Lambda is equal to lambda to the power k times e to the power of negative lambda all over k factorial. Applicable to counting occurrences in time or space, arrivals, defects, mutations, foundational for statistical physics, and modern probability modeling. I mean, it's kind of what statistical physics is, right? I mean, I was kind of redundant there, I guess, but that's fine. I mean, because that's way more specific, and I just feel like it should be mentioned. Okay. 8. How can the Earth's gravitational attraction be modeled? There's lots of ways, but let's look at Legendre and Laplace's ways, shall we? Legendre derived zonal harmonics to model gravitational fields of ellipsoids. Laplace introduced the potential function. Come on, let's get this going here. Set up to include here, and I'm going to include this as that box here. Disputed territory, there we go. Okay, so zonal harmonics. to model gravitational fields of ellipsoids. Laplace, potential functions. And Laplace operator. Their work unified celestial mechanics, fluid dynamics, electrostatics under a common analytical framework, providing mathematical foundation for geodesy, astronomy, field theory. So let's move on to the final piece here, which is the closing dialectic. The French Revolution shaped mathematics, not merely by content, but by context. It redefined several things. Institutions collapsed, and from their ruins emerged the first state-engineered curriculum for mathematical power. Geometry became tactical. Analysis became systemic. The École Polytechnique, with Monge as its artifact and Lagrange as its high priest, in a sense, became the axis around which the next half-century of instruction would rotate. For a time, Paris stood unmatched. Laplace rewrote the heavens and equations. Lagrange reconsecrated mechanics and symbols. Cauchy made rigor a virtue. Fourier gave irregularity a voice. Legendre and Poisson redefined number, probability, and potential into tools. But empires of thought, like empires of state, do not endure without renewal. And so there's several reasons why French ascendancy waned. Educational ossification. The École Polytechnique became doctrinal, its lectures memorized, its innovation dulled. The very formalism it birthed began to constrain. Philosophical singularity. So where French mathematics aimed at completeness and clarity, German mathematics, as we'll see here later, turned toward abstraction and infinitude. And here's the third thing: revolutions, the aftermath of the revolutions. So while France struggled with waves of political upheaval after 1830, Prussia and England invested in long-term academic form. So it gets them some catch-up time anyway. Lack of successors. This is just, yeah, so after Cauchy, few French mathematicians matched the originality of their predecessors for this time period. Meanwhile, Berlin and Cambridge cultivated a new generation of theorists. A rise of successors from these places that I mentioned: England, the Analytic Society, with Peacock, Herschel, Babbage, Charles Babbage, which is a very famous name in regards to computation, broke free from Newtonian isolation, re-imported continental rigor, and laid groundwork for symbolic algebra and computation, as I mentioned earlier. Prussia, Guass, Dirichlet, Jacobi, Riemann, extended and surpassed the analytic groundwork laid in Paris. Berlin became the new capital of abstraction, function theory, number theory, and geometry, reimagined. Journals and institutions. While France had the École, geometry built a research university model, flexible, diffuse, and generationally sustainable. So the revolution gave mathematics new instruments, but it was the next century that learned to play them better. France, in the revolutionary era, transformed mathematics from guild to grammar, from a scholar's pursuit to a state language. But it was in Göttingen and Königsberg, in Cambridge and Berlin, that mathematics became philosophy again. And so we turn to chapter 19, which is on a very big name, Gauss. Carl Friedrich Gauss specifically. This is going to be the long lecture, which is fine. It's just, it's probably the longest, this is probably going to be the longest lecture in the series, but it's like the shortest amount of time, which is interesting, which just sort of reflects that skyrocketing rate I mentioned earlier. So the time period that we're looking at here overlaps a bit, but we're focusing on Guass, which is 1777 to 1855. So late Enlightenment, Romantic rationalism, Goethean ascendancy. There's a whole bunch of notable figures, of course, that first of which being Carl Friedrich Gauss, Johann Carl Friedrich Plauch, Sophie Germain, which is one of the first, she's one of the first really big female mathematicians. Joseph Louis Lagrange, Adrien Marie Legendre, Frédéric Bessel, Wilhelm Weber, Evestri Galois, Bernhard Riemann. These are the names which make up this era in the main. So mathematics for Gauss, we'll see here, was not an escape from reality, it was the reformation of it. You know, you see like cloisters of mathematicians and whatnot, there's this sort of image of them being in an ivory tower, in a sense, detached from everything else in here. Which, you know, is one way you can do it, but not for Gauss. He was no mere calculator of numbers, but a sovereign of structure, raised in the shadow of Kant and Euler. Gauss emerged not as a product of Enlightenment optimism, but as its silent heir, measuring planet, forging number theory, and unifying domains not by decree, but by silent, certainly not by decree, but by silent exact dominion. His time was not yet where we now stand, but through him the present age of mathematics was born quietly, precisely, eternally. Something special to mention here. There's this interesting parallel of civilizations in between the old Swiss Confederacy and what would later become Germany. The old Swiss Confederation was not a precursor to Germany politically, but philosophically and culturally. Its structure, which by the way, why am I mentioning this? Well, Euler came from the old Swiss Confederacy, right? And so these two big names, Gauss and Euler, which would come to really define, they're kind of like you have Leibniz and Newton up there, and then you have Euler, and then you have Gauss, right? These big generalistic, universalistic mathematicians. Gauss was German, very German. Before Germany, of course, there's Germanic peoples and Italian peoples before those things ever became unified. That's not an argument. But the old Swiss Confederation was a precursor to this. It was a decentralized federation of cantons, mostly German-speaking, Protestant-leaning, and fiercely independent. You see the same thing for Germany. And so the old Swiss Confederacy is kind of what Germany would later become in microcosm. It's home to precision, restraint, and rigor, mathematical rigor, with Euler, with Zwingli and Calvin, theologically speaking, and legally speaking. Versus like the Dutch Republic, which is like a microcosm of proto-France collapse within their Enlightenment. This Jean de Witt, which we mentioned earlier, who was eaten by his own people, which is terrible, but you can understand why they were angry at him. He spoke in abstractions while the people suffered military disaster and economic collapse. And that's sort of, that's a correspondence to what happens later on in the French Revolution. They detached themselves from these sort of axioms that had long been established within the monarchy, and then tried to reestablish something on lines of pure reason, which Kant has a critique of, in a sense, and so it leads to barbarity, which is, one would argue, man's more natural form. But back to the math of the thing. Let's look at the big pictures. The big pictures of what this civilization looks like. So there's this interesting thing about Gauss is that, it's like how there were Soviet cosmonauts who went into space and then they looked back and their country was no more. The Soviet Union fell in 1991 while there was still cosmonauts in space. Gauss lived through 3 iterations of a German nation, one being the Holy Roman Empire, the HRE, which I'm not going to draw too much here, but just a little bit. Now, its boundaries are wacky, to say the least. This is sort of a 1796 approximation of the HRE. And then you have like this little Confederation of the Rhine, which is basically just a Napoleonic puppet state. The Confederation of the Rhine. Its borders roughly in 1812. And then big, chunky German Confederation. And this is roughly in 1815, which they kind of get all of their old stuff back from the days of the HRE, but it's a bit different with what's going on here. That'll become a bit of a problem, but that's fine. It's not fine, because later on, a lot of people will. It's neither here nor there. Okay. It's fine for today, because we've overcome a lot of that. So Gauss did not live in Germany as we know it today, of course. He lived in a long prelude to it. 3 regimes, fragmented sovereignty, 1 language. In one particular language, mathematics. So mathematics, in a way, becomes the it already is, but it's the supranational language. In a time when German lands were politically fractured, Gauss's mathematics spoke across borders. To the French, with his contributions to number theory, complex analysis, and geometry, Gauss matched and rivaled Legendre, Laplace, and Cauchy. To the British, his astronomical precision and silent rigor paralleled Newton's legacy and extended it. To the future, by avoiding nationalism, he seeded a universalist mathematics that could be inherited by Dirichlet, Riemann, and others. Gauss didn't carry a flag per se, though he was German. He carried a structure, more so, silently sovereign, mathematically eternal. So let's go over some of the periods in the life of Gauss, insofar as we know it. And insofar as it, well, yeah. So Carl Friedrich Gauss was born in 1777, sorry. 1777 on April 30th in Brunswick, Germany. And not exactly a wealthy family, as you would really expect from mathematicians of most any era, but to a modest family with little formal education. Yet by the age of 10, Gauss had already revealed an instructive mastery of number. There's a famous instance, his instantaneous summation of the integers from 1 to 100. It's not a parlor trick. He had figured out this amazing summation, and this was really his signal that mathematics, that he was going to be this sort of monarch of mathematics in a way, in the same way that Euler really was, in the same way that Isaac Newton was, in the same way that Leibniz was, right? So from 1788 to 1795, he was supported by the Duke of Brunswick, which is like, supported by a duke. You know, at this point you can kind of say whatever you want if you're supported by a duke, other than things that go against the duke. He studied at the, let's go ahead and, Collegium Carol Carolinum. Probably this Carolin probably comes from the Carolingian Empire. Can't be certain. Well, could be certain. I'm not certain because I I didn't look into the etymology, I guess, of this thing. And then he studied at the University of Göttingen. Göttingen. Now, he was just a teenager, while he was doing this stuff. He proved the constructability of the 17-gon using only compass and straight edge in the way that, the Greeks would have preferred him to do it. In 1799, he gained his doctorate at the University of Helmstedt. With a new proof on the fundamental theorem of algebra. Emphasizing the necessity of existence, not merely calculation. In 1801, he was 24. He published Disquisitiones Arithmeticae, and it was a magisterial work that would reforge number theory and lay dormant for decades before bearing its full legacy. Which, by the way, is just a theme in the life of Guass. He's gonna tuck papers away and not talk about things. Just kind of really, it's gonna be like every dragon in fiction ever that hoards gold, but definitely not a whaler. Definitely not the way a whaler would have done things, but he's Guass. From 1801 to 1807, in a demonstration of computational brilliance, Guass calculated the orbit of the lost asteroid Ceres using only a few observations. So you looked at it a few times and you were like, yeah, that's where it's at. I calculated it. Aren't I clever? Yes, Guass, you are clever. Calculated was clever. Calculated orbit of Ceres. And this sort of ushered in his role as both theorist and astronomical tactician in a sense. Like I mentioned earlier, he's not one of those guys that not one of those mathematicians that's just it's your theory, I'm gonna hide over here and just look at that because that's the way I do things. Which is fine, it's just, it's me mode. Okay, 1807 to 1855. In those years, he was appointed the director of the Göttingen Observatory, and Guass spent the rest of his life using number theory, astronomy, physics, geodesy. Despite personal tragedies, some things like, were out of his hand, and some things were very much in his hand. And institutional constraints, just like everybody has, his productivity and precision endured. He was a reclusive person, Guass was, but his mind moved across disciplines with sovereign confidence, like he was a traveler, a conqueror, as some would call him. He proved theorems silently, recorded discoveries cryptically, and often published only when pressed. His diary, begun at 19, chronicled revolutions in silence, nearly all of them without fanfare. Very German, very German. At least a lot of people would say very German. I imagine his sense of humor was very literal, but who knows? Somebody probably knows. Okay, so some of his foundational contributions, first of which we'll go over here is number theory, in number theory I mean to say. This was done mainly through the mentioned work, this Quaestiones Arithmeticae in 1801, as I mentioned in the timeline. Now here, we'll get more specific. He introduced modular arithmetic, congruence classes, residue systems, or slash remainder, I guess. I mean, residues, that's a lot more generalizable, I guess. He proved the law of quadratic reciprocity. The theorem Orem, calling it the gem of arithmetic. Gauss has this phrase where he says that mathematics is the queen of the sciences, number theory is the queen of mathematics, and so far as he can tell back then, and he's the king of mathematics at the time, so who can say otherwise, He's gone now, so you talk real crap now that he's dead, but it's like, when he was around, it's like, oh no, he's the king. It's just the way humans are, Law of quadratic reciprocity. Developed the theory of binary quadratic forms and cycloatomic equations. So really cool looking things. Talking specifically about cycloatomic. Like, that's a cool name. Like, I feel like that would be a thing in the 90s. You look at like a Transformers episode and you'd find like somebody called like, this is my cycloatomic ray gun or something. It's like this big thing that shoots circles. It's like, but no, cycloatomic equations is a very different thing. I mean, it has to do with, circular looking things, but that's just because the way it is. Not my believers. Could be. No. But he defined Gaussian integers and extended the fundamental theorem of arithmetic to them. So, and there's this interesting thing which he did at the age of 14, which is formulation, like a formulation of the prime number theorem. What was I doing at age 14, right? Certainly not that. Okay. Probably just use this marker for this instance, then I'll probably have to toss it. Toss it now. Oh. Right. So, provided the first rigorous proof of fundamental theorem of algebra. Basically, I can't. So basically every non-constant, every non-constant polynomial has a complex root. And he published 4 distinct proofs in his lifetime here, which would and these refine the existence as a core algebraic principle. Right. Now, another thing he influenced: geometry and constructibility. Right. So, as I mentioned earlier, he constructed a regular 17 gun. with compass and straight edge. You know, isn't that much of a... It's not like labor-wise, it's like that's, you know, it's not like he's like tilling a field or something in a feudal crop, but I mean 17 lines. No. No. I mean, like as a child, right? You know? I mean, did he even really get a childhood? It's like, hopefully. Though, I mean, doesn't look like he did. Okay. Compass and straight edge. That was really the first new polygon. First new real such polygon. New such polygon, that's important. Since antiquity. What else did he do? Well, he proved a general theorem of which regular polygons are constructible. So basically it's like those polygons whose number of sides is the product of a power of 2 and distinct Fermat primes those are constructible with straight edge and compass. So yeah, you can sort of see this unification of classical Greek geometry with modern number theoretic thought. You're blending Fermat primes and straight edge and compass. So great magnificent thing there. But you know, it's very much the way that some of the best works are produced, to blend in between tradition and modern. Too modern, it's probably too shallow. If it's too traditional, it's probably just probably doesn't have much difference from what they were talking about back then. Now, here's another thing, which is his contribution to astronomy and orbital mechanics. We saw there earlier from his life, he could just look at things with a few observations and just go, yep, this is where it's at. And this is kind of what we see with Gauss's method of orbit determination. So you can look at the way, you can look at a few variables and determine, yeah, that's where that's where the object is going to be in orbit. He successfully, yeah, I mentioned this earlier, but yeah, he predicted the rediscovery of Ceres in 1801. He published a book, Theoria Modus Corporum Celestium, in 1809. So in 1809, this book standardized orbital mechanics. So you can really see this is really the era of standardization, I guess you could call it. It's like 18th, 19th century stabilization. So really the 18th. Orbital mechanics. And this guy just keeps on going, right? So, let's see here. What else did he do for math? Well, with differential geometry, which, largely comes about in 1827, his stuff in 1827. He introduced the notion of the Gaussian curvature. Which K is equal to 1 over R, little r times big R, a local invariant of surfaces. He developed intrinsic surface geometry using the first fundamental form. Which is, just let me get to it here. Intrinsic surface geometry. Which utilize this first fundamental form, which now is EFG, right? Energy, force, gravity. I think that's, yeah, either way it's EFG. Yeah, okay. Proved the theorema egregium, which is that curvature is invariant under local isometry. Very important. And this would really become important for theory of relativity stuff. Like that really led to this another wave of popularization for differential geometry was the theory of relativity. So much so that afterwards, I recall Einstein was like, the mathematicians took my theory and now I can't understand it. Which is funny joke, but also it's like, yeah, they'll put it in the system and they'll rigorize it. Rigorize it? They'll put a bunch of theory on top of it, which comes from, all the way back here and before, right? So, yeah, and Gauss laid the groundwork for Riemannian geometry. You have a Riemann sum, which we'll get into later, and modern manifold theory. Right. So what did he do for complex numbers? There's also this thing called the Argand plane. It's also a neat thing. We're just discussing it briefly though, so I'm not going to get too much into that. So he formalized the complex number plane. Which gave a geometrical reality to imaginary numbers, right? Because, I mean, like, that was the thing. We talked about that earlier, about how, like, complex numbers, not really a readily acceptable thing. And then they just sort of slowly became a thing. Well, this is part of that slow rise of, this is a real thing. Complex numbers are. Like, here's a complex number plane. You can look at it, geometrically, feel it in a sense. So, he introduced the term even, the term that we use today for complex numbers, which is complex numbers. And he treated complex numbers as a complete field with visual structure. Okay. Last but certainly not least, we'll mention his influence on potential theory and magnetism. Magnetism. It's like capitalism, socialism. You know, it's an economic theory. No. So, which capitalism isn't really a theory. It's just kind of what humans do. But anyway, co-developed the theory of potential with Wilhelm Weber. I'll just call him Wilhelm Weber because it's a W and I'm American, so that's just how things are. Theory of potential. Sorry. Not sorry. But I mean, like, I don't know. There's a proper way of saying this. This is Wilhelm Weber. I was just thinking of Wilhelm Steinmetz, and it's like, oh, he became American, and it's like he preferred it, right, to be pronounced that way as Wilhelm Steinmetz. Two different Wilhelms, though. So, he applied mathematical rigor to electromagnetism, gravitation, and geophysical modeling. And he introduced the principle of least constraint. Somebody can write a spicy novel based on physics called The Principle of Least Restraint, but I'm not going to get into just thought of it. Goodness. Okay. Contributed to capillarity, and field theory. Field theory. Not unified field theory, just field theory for now. Just field theory. We're not going to unify them for now just yet. Okay. So, what are some of the canonical problems and solutions that Guass contributed within this larger framework of these mainline contributions that we discussed more in general? Well, let's look at problem 1. Can every polynomial equation be solved in the complex plane. So, Guass said yes. Guass said, yeah, that's possible. He proved it. He proved the fundamental theorem of algebra. Which every non-constant polynomial with complex coefficients has at least one complex root. He returned to the theorem 3 more times in his life, refining existence into rigor. But yeah, that's what he found there. Back in 1799. Now, another question. What governs the solvability of Diophantine equations? Diophantine equations and modular convergence. Congruences. So, Guass found the law of quadratic reciprocity. First published in the Disquisitiones Arithmeticae, it describes the conditions under which the congruence x squared is congruent to p mod q is solvable. If P over Q times Q over P is equal to -1. And this is the weird part, right? P minus 1, Q minus 1 over 4. So, Guass called it the theorem aurum, the golden theorem. Which, shows how much he thinks of number theory, right? If he's able to find this big thing in number theory, he'll call it the golden theorem. And that he sees it as the queen of mathematics. So the number theorists basically, this was their age. This was the age of the number theorists, right? if ever there could be an age of the number theorists, it was under Guass. So there we go. Now, next question. Can we recover the orbit of a celestial object from limited data or data? The answer is yes, of course, because Guass is a genius. And he found it with, I'm not going to get too much into it, but Gauss's method, just, look into Gauss's method if you're more interested in that. Gauss's method, orbital mechanics. That's where you'll find it. Also, I think it's pretty funny that in this part of the textbook, like Gaussian elimination isn't really mentioned all that much in this textbook, but like it's kind of his thing, but also kind of not, because we talked about it earlier with the Chinese having their own thing, which was basically Gaussian elimination from way, way back in the lecture material. But anyhow, now next question: which regular polygons are constructible? With compass and straight edge. Well, ladies and gentlemen of the audience, those whose number of sides is a product of a power of 2 and distinct Fermat primes. Good job, Guass. His own construction of the 17-agon, as you remember from in 1796, was the first new such construction in over 2 millennia. It's like, that's crazy. That's crazy. It's been 2 millennia, and he manages to find this thing. Which, it's like, to be fair, it's not like it was a unified, coordinated effort to try and find this thing, but just something original in mathematics in 2 millennia. That's pretty good. That's really good. What is the intrinsic curvature of a surface at a point? Gauss's answer? The Gaussian curvature. Gaussian curvature. K is equal to 1 over little r, big R. And this is from his theorem, egregium. It's an intrinsic variant, unchanged under. Yeah, that's important. Intrinsic variant, unchanged, which is a big deal if you're looking at topological stuff. Unchanged under bending. It's less of a big deal than some other things, but it's a big deal anyhow. Now, are imaginary numbers real, right? Not like real numbers as in real, but just real. Do they exist? Are they a thing? I mean, you can't empirically hold an imaginary number, right? You can hold a printout or a construction of an imaginary number, but you can't hold an imaginary number, right? So, it's like, Guass says, in the plane with no pilot. No. In the plane, he formally defined the complex plane as bold script r squared, which is a real number, 2 dimensions, I guess. It's a more precise way of saying that. Okay, with coordinates A, B, which would represent A plus B, I. The plane of complex numbers is still called the Gaussian plane. To this very day. No one flies on it. I mean, technically, people fly on it. No, they fly on a real plane. Yeah. That's hilarious. Okay. Just in a different way. It's not the same plane. Oh. Okay, so how should we model physical fields according to Gauss, like gravitational, magnetic, electric? Gauss says via potential theory. Who's going to stand up to Gauss? It's like absolutely no one's going to stand up to Gauss because Gauss is too on it. He defined potentials as scalar fields. That's important. Whoops. Yeah, potentials as scalar fields. With gradients, whose gradients yield physical forces. With our powers combined, we have contributions to electrostatics, magnetism, geophysics. I can write all that again because I already did. Okay. Now, let's see what all of this means in terms of Gaussian legacy, right? What is a legacy but that which you're remembered for after you're gone? And in this case, Gauss did not inherit a universalizing system of mathematical foundations from the days of Euler, but rather the legacy of Euler expanded in parts, right? So he constructed one such universalizing system similar to how Euler had built his body of knowledge with the age that came before him, right? This war and trident between Leibnizian and Newtonian calculuses. Stone by theorem, line by convergence, orbit by calculation. The first of his contributions, which carry on into the influences that he had, are Gauss, or at least in terms of how he's remembered. Gauss as architect of modern number theory. It's like, you know, the first thing I thought about whenever I thought about Gauss, just like without designing the lecture, before I even, you know, read this chapter in Boyer's textbook, the one thing, you know, that comes to my mind, the first and one thing that comes to my mind about Gauss is number theory. And that's not for no reason. You know, he unified modular arithmetic, congruences, quadratic forms, and cyclotomy into a rigorous symbolic architecture, right? So his disquisitiones arithmeticae became the foundational text for Dirichlet, Dedekind, and Hilbert, which we'll talk about later, each expanding its depths into analytic number theory, algebraic integers, and class field theory. What else? What else do we sort of contribute largely to Gauss? Well, as a silent catalyst, most definitely. He's not like Euler or like Leibniz. He's his own thing. He's more akin to Newton, I guess you could say. He rarely published fully. Many discoveries remain cryptic, coded in diaries or unpublished manuscripts. He inspired future giants through fragments, really. Riemann in geometry, Jacobian elliptic functions, Eisenstein in primes, but he was very, you know, sort of cloistered. He didn't really like people, which is, it didn't really seem like it anyway. So there's that. He was estranged by one of his children, you know, so he had people problems. He had people problems, so Gauss did. And also, he's credited for revealing a lot of fault lines, you know, similar to just the way that great geniuses do, right? I mean, so despite his foundationalism, Gauss has left key structures unformalized. Limits and continuity lacked epsilon delta rigor that we have to this day. Imaginary and complex numbers needed algebraic foundation still. Elliptic and modular functions were left largely undeveloped. Now these would become battlegrounds in the 19th century for analysts and algebraists to debate and build over. And as I mentioned earlier, he of course has, his intellectual proteges, his mathematical proteges in Dirichlet for number theory, Riemann for geometry, Eisenstein for modular forms and prime behaviors. Galois and Abel, they were independent, but they reflected the structural and algebraic vision Guass had founded. So, and his influence endures to this very day. In notation, planetary motion, in the definition of curvature, in the field of complex numbers, in theorems carved into the bones of algebra, Guass still remains. His silence wasn't a void, it was potential of what could be left to others to build. Whether or not that silence is more a thing of temperament or actual, gift, willing gift, who could say? Who could say but God alone? So Guass did not trumpet his discoveries, he engraved them silently, deeply into the foundation of modern mathematics. He was not the loudest voice of his age, he was the voice through which the age became architecture. Where Euler harmonized faith and analysis, Guass forged silence into sovereignty. Where others published in pursuit of glory, Guass wrote for eternity. And often withheld even that. He believed mathematics was not merely about truth, but about precision worthy of that truth. He stood at the hinge of centuries, the last great solitary mind of the Enlightenment, the first foundation layer of modern number theory, geometry, and physics. His theorems were not reactions, they were formations of space, of number, of motion, of meaning. Mathematics is the queen of the sciences, he said, and number theory the queen of mathematics. Guass wore no crown, he needed none, he built the throne itself. Okay, so now we get into this part of the lecture which turns to three separate branches which would emerge into the modern day. So that's going to be, So that's going to be 20, 21, chapters 20, 21, 22, which I'll discuss in brief, though not in the full depth, which they perhaps deserve, but, you can read the book, right? You'll be fine. Which I can actually So we'll do this. How about this? We'll approach core problems of each of these three branches and discuss how iterations of that field would approach that problem. Okay. Here we go. So, we're going to start with geometry first. So let's ask ourselves this core question. Given a curve, what is just organize that. Given a curve, what is its nature? Which is such a broad question, right? I mean, it's broad enough for iterations of a single field. of knowledge. What is its nature? So keep this question up here. I shall draw it like the borders of Oklahoma because that's just the way it turned out. Panhandle and all. So for Euclidean geometry, a curve is something constructible with compass and straight edge. Which all of this will kind of be roughly speaking, because, I mean, except for this is kind of like, this is almost verbatim, it's like, yeah, this is how we do things, compass and straight edge. If it's not compass and straight edge, we don't want anything to do with it. It's like, okay. So, given a curve, what is its nature? A curve, something with something constructible, with compass and straight edge. Its nature, then, is captured by steps needed to draw it. So an example of this is conics. So a conic is known by its geometric definition, with ellipse equaling a locus of points with a sum of distances. So let's just kind of call it a day for now. Yes. Now, let's approach it from the perspective of way later, which is descriptive geometry via Monge. Okay, and that is curve as 3D object. It's in 3D, man. It's super cool. Whoa. Projected into 2D views. Its nature lies in reconstruction. The solid it belongs to. Solving it means unfolding space into plan and elevation. And that's it for descriptive geometry for now. Because all of this stuff is just, it's developed so fast. Like a lot of this stuff is just, as you can say, like, it's, as you can see rather, it's, these are entire classes, right? So, courses of information, it's just, so, and we're just covering the surface for historical purposes, right? So, projective geometry. So, by that, what is a curve? It's part of a system. It's part of a system. Part of a system of intersections, tangents. I should note. Yeah, these big names, which we won't be able to cover more thoroughly. Poincaré. So he's, so a big part of why we have this projective geometry here. A curve is a part of a system of intersections, tangents, points at infinity. Now, what's its nature then? Its nature? Well, something that can be captured by invariance. So something like cross ratio. That persist under projection. So you can kind of see how the underlying, what would the thought process of what would later become topology perhaps emerged. It may contain ideal and imaginary points that ensure completeness. It's like not. I mean, this isn't the point, but it's like, not only can we imagine it, not only is it real in terms of the way in which we can construct it, but in any possible way you can imagine it. Okay. Now, apart from Euclid, like as I noted earlier, all of this stuff is happening in this time. So, it's like 18th and 19th century, late 19th century, to the late 19th century. Yeah, okay. Then we have analytic geometry. There's different colors of geometry under the sun. Is Pluker, Cayley, who's also, very important. So what's a curve? A curve is an equation in coordinates, from this perspective, roughly speaking. And what is its nature? Well, it's algebraic. Defined by degree. Degree, singularities, and symmetries. It is studied through its dual, the family of lines tangent to it. It's dual, like not a duel, but a dual, like two things. Or you need two people in order to have a duel, but you can have a duel between three people, right? It's kind of weird. Why would you do that? It's more like a standoff. Anyway. Onto Riemannian and algebraic geometry. Riemann, of course, and Klebsch. A curve, well, that's just a manifold. Possibly complex. Possibly with symmetries. With singularities, sorry. Goodness gracious. Singularities, what am I doing? Its nature? Yeah, we're getting closer and closer to just, outright saying topology, but I mean, one of the key things there is like it's defined by its genus, which is how the argument goes. I mean, the joke goes that it's like a coffee mug it corresponds with a torus because of the genus 1. So, genus 1, genus, function field, and moduli. To understand it is to classify it among families of curves with shared invariants. What began as a figure now becomes a function space. What was once drawn is now abstracted, not erased, but refined. So, how that be? Okay. And then up next we have algebra. Which again, in the same sort of questioning manner as earlier, we will approach this subject as well. So let's suppose we're asked the question, given an equation, what does it mean to solve it? So, arithmetical algebra, this isn't even going, so this isn't going as far back as algorithmy, which we talked about way earlier. We're just going to go and cover sort of like a modern algebra, starting with Peacock in, I think, roughly the 18th, 19th century. Let me see. Here, just to make sure I have that right. Because I wrote it on here, I'm not sure. 19th century? Yeah, I think that 19th century. Yeah, we're just going to cover like modern algebra in terms of 19th century onward. But this isn't even going back as far back as Al-Khwarizmi, the way that he probably would have seen things, right? So, arithmetical algebra. Yeah, this was this guy's actual name, right? Pretty neat. I wonder if he was ever seen as prideful. That would be hilarious. He's too prideful. Okay, so so mean. Okay, equation is numerical statement. What does solving it mean, right? Means finding a number, right? This is sort of like what everybody thinks algebra is sort of thing, right? Really, they're talking about arithmetical algebra. The symbols behave like numbers and must obey their rules. Formal symbolic algebra. De Morgan. Boole. Check the camera real quick because I don't want to not capture anything. Happening once. Okay. So an equation is a formal expression. So yeah, the linguists are starting to get involved, which is pretty interesting. Like, so this is an interesting thing within the history of algebra. A lot of the stuff that's built in the 19th century actually emerges from people who are it's a lot of British folk, actually. A lot of British folk, and a statistically significant number of Irish individuals, such as Boole. And they happen to have a history in studying linguistics, or for that time, philology, which is, you know, sort of what Tolkien studied that. So that's interesting. How mathematics as language really kind of is built here in algebra. Equation, formal expression. What else? Solving it? What does that mean? Well, in the case of formal symbolic algebra, it means transforming symbols according to its internal rules. Not interpretation. The solution is structural, not numerical. So, algebra is logic. That was a debate that also emerged, like is mathematics and the formal field of study of logic. Can it be said that logicians and mathematicians are part of the same body of knowledge, just at different ends? And that was a enormous debate. It's kind of like, you know, it's been settled now where it's like, yeah, in a way, roughly speaking, that's the general gist of what I get of the, because we're at the edge of what's happened, so it's hard to say for sure, but it's pretty certain. It's like there's a pretty strong indication that most everybody accepts that, like, you know, if you have to put it up to a vote, I don't know, but I think I'm pretty sure that people would say yes. Yes, they're part of the same sort of thing. You can root mathematics and informal logic, and then that into logic proper. So, but anyway, what is an equation? Well, an equation is something which encodes a logical relation. Right, okay, so And what does solving it mean? It means checking, truth preserving, inference. Variables stand for propositions. Operations stand for reasoning. Now, algebra as structure. Hamilton. Not that Hamilton, the other Hamilton. The math Hamilton. He's not going to get up and start singing. Thank goodness. Not that I don't like singing, it's just that sometimes it can just become so overplayed, overdone. What is an equation by this idea of algebra as structure? It may live in a non-numerical system. An equation may live, it's a thing which lives in a non-numerical system. Like matrices. Or quaternions. What does solving it mean? It's contextual. Depends on the system's laws. Now, algebra as foundation. And this is very much in the way of Dedekind and piano. This is definitely our most recent development. An equation, it's a part. It's a part of an axiomatic system. What does solving it mean? Derivable. It's what follows from definitions and axioms. Algebra becomes a logic of system building, from number to symbol, from computation to transformation, from solving to structuring. Algebra no longer solves equations, it defines the worlds in which equations exist. Right. So with analysis, we'll ask ourselves the question, what does it mean for a function to be or not to be continuous? So, pretty rigorous intuition. Starting with Euler here. So, a function is continuous if it can be drawn without lifting a pen, right? That's, yeah. That just sparked a whole bunch of memories I had, again, when I first learned about continuity. Just in high school, calculus, it was just a good memory. Continuity is geometric notion, obvious when seen, right? So, then we have Cauchy's reformulation. So a function is continuous if the limit exists and equals the value at a point, at the point in question. It's continuous at a specific point. So it's formulated using sequences. Continuity as limit preserving. Still grounded in geometric intuition, mind you, but it's way more formalized than just, you can put a pen, and if you don't, you can draw with a pen, if you don't lift it, it's continuous. It's like, well, this is better. This is more precise. Intuition is good for pedagogy. It's bad for precision. Usually, unless your intuition is very precise, which is a different kind of intuition. Oh, almost wrote that again. Okay. Weierstrass. Here we go. Here's something that looks a bit more modern. Weierstrass's epsilon delta definition. So, a function is continuous if for every epsilon greater than 0, there exists delta greater than 0 such that there's a whole bunch of other stuff that you write over that, but that's not the point of this. The point is just to look at the overview of the thing. Historical, you have to be careful because if I go too far into the mathy side of things, you lose a lot of the time that you would have spent on the historical breadth of the thing. So, anyhow, Weierstrass's epsilon delta definition: for every epsilon greater than 0, there exists a delta greater than 0, such that this framework admits strange functions, continuous, nowhere differentiable. That runs into the problem of Dirichlet's. I think it was Dirichlet. Yeah, Dirichlet's Dirichlet function. There's this Dirichlet function in which it's continuous everywhere, I think, but it's like it's differentiable nowhere. So that leads us to Riemann's perspective. You know, and because like I didn't go into it further because there's like different forms of continuity that arise out of Weierstrass's definition. So we'll just sort of leave it at that. Riemann's perspective. So, continuity is examined in the context of, so before Weierstrass, by the way, that's like continuity is a local definition defined without reference or motion to a graph, like neighborhoods and stuff like that. So, Riemann's perspective, continuity is examined in the context of integration and complex analysis. Sometimes discontinuous functions are integrable. The nature of discontinuity matters. Continuity becomes one aspect of analytic structure. So what is a continuous function? It's simply, just one aspect of analytic structure. Structure, it depends, because it's more algebraic, right? It depends on the context. So there's like Lebesgue integrals and Riemann integrals, and you're going to need to know those and what sort of, which is just a whole other thing. I mean, Riemann integrals are the ones that you basically see all the time. Lebesgue integrals are the ones that fancy mathematical people usually turn to. So, interesting way of putting it. Very good. Okay. So, this guy by the name of Cantor, and he has a set theoretic view. And so, what is continuity then? A function that is continuous. Well, it's continuous if it has a different sort of context to it. Like it's about behavior of pre-images. So it's like if it's kind of like invertibility in a way. Behavior of pre-images of open sets. So it's like if every pre-image has an image, so that's kind of like that's invertibility. So it's kind of like that's more in line with invertibility. So let's just say behavior. It depends on the behavior of pre-images to open sets. It introduces an idea of pointwise versus uniform convergence. Yeah, which is what I was sort of getting at earlier there with Riemann stuff, which we won't get too much into. It distinguishes between countable and uncountable sets of discontinuities. So if that's something which interests you, the diagonalization argument, which basically it's like, there's two different types of infinity in the main, which is like, there's like the real numbers. So it's like, it's not true that these things map to the real numbers. And the reason for that is that, you can find a real number such that for every natural number that exists, there's a real number that a natural number cannot map onto. It's an interesting argument, the diagonalization argument. Finally, we have Poincare. Which is continuity is no longer a guarantee of predictability, qualitative behavior, like the shape of the thing, right? It's sort of like it's an interweaving between, this analytical framework and geometric intuition. So continuity is no longer a guarantee of predictability, yes. Qualitative behavior, it's not just limit behavior, it becomes qualitative behavior. Yes. Dynamical systems exposes sensitivity within continuous flows, as I was mentioning earlier. A function is continuous as such that the case of qualitative behavior that we can see illustrates it as such. Is the best way I can sort of say it. There's like fixed points and like saddle points, and it's a whole thing. Dynamical systems is a good example of that. Looking at something more qualitatively, the way that Poincare would intend. From visualization to limit, from limit to formal logic, from logic to abstraction to chaos theory, which is what dynamical systems is sort of the modern, it's the modern heir apparent to chaos theory back then. Continuity survived each of these shifts, but its meaning never stayed fixed, like the points that Poincare would later look at. So now we get back to the main line, a main line, in which we discuss 20th century legacies on this. We're getting pretty close. We're getting close to where we are now. Today. So, this is chapter 23. Man, that would have been cool if you could have used chapter 20th century legacies, right? 20th century Fox. 20th century legacies. I built a legacy once. We all leave a legacy. It just depends on how great or how small or what point. For good or for evil, we do not know until the end, though we can see it in belief. Now, 20th century. Circa 1890, 1990, Clinton administration. Oh no. Okay, so some big names: Henry, Poincare, as I mentioned earlier, David Hilbert, Bertrand Russell, Emmy Noether, L.E.J. Brouwer, Felix Hausdorff, Jean von Neumann, Alan Turing, Nicholas Bourbaki, Alexander Grothendieck. So the 20th century, it didn't inherit mathematics in so much as it did, of course, every generation does, but it restructures it a lot more. We'll get into what I mean by that, I think, a lot more here in just a moment, but institutions expanded, so we saw that sort of happening within France. Notations evolved, abstraction crystallized from the ashes of war. World War I and II. In the ferment of foundations, came to mathematics no longer provincial or partitioned, but global, formal, and conceptually interlinked. A new kind of power emerged, the ability not merely to solve problems, but to define the very framework in which problems could be understood. Poincare bridged physics and philosophy. Hilbert recast geometry, logic, and number theory into axioms and problems. Lebesgue and Borel redefined integration through measure. Noether turned algebra into language. Bourbaki rebuilt the edifice in structural, glass, and from logic's edge, Gödel declared what could not be proven, even in the most ideal of conditions on earth. War, migration, and exile scattered minds. These birthed new fields of reasoning. Topology became algebra became category, computation became density. The pure collided with the practical. Turing machines, atomic structures, cybernetic loops. This was not merely mathematics as it had been. So mathematics is architecture, recursion, resistance. Check that. So we don't have too far to go. So, some of the faces of the error on the Reed Poincaré. (1854 to 1912), mentioned in passing there. He is the founder of algebraic topology. This comes from his work, Analysis Cetus, and he coined these big complicated things, well, kind of complicated things, which are Benny numbers. And fundamental groups. You know, they're fundamental. Okay. He developed automorphic functions. Zeta fusion systems. And as we mentioned earlier, you know, we'll just call it dynamical systems because that's essentially what yeah. Qualitative analysis of differential equations is essentially, can't do it. Okay, so we'll just, because I mean, differential dynamical systems would come of its own sort of thing and be just really rooted in probability theory and statistical mechanics of group actions. So we'll just say qualitative analysis of diffie-Qs, man, diffie-Qs. Okay, he authored vast work in celestial mechanics. Chaos theory. Mathematical physics. And he bridged science and philosophy with popular writings and a universalist mindset rivaling even Gauss. So he's some people call him like the last of the universal mathematicians. I don't know. It's kind of hard to say. It's like how far can human intellect possibly go versus how much are we able to build? You know? So it's like how much in comparison to yeah. So it's like von Neumann kind of comes around later, and it's kind of like it's arguable. It's arguable that he was kind of a universalist, but that's a different debate. David Hilbert, 1862 to 1943. Oh, Poincaré didn't live to see the Great War. He died at the peak of the British Empire, at least economically speaking, I guess. 1912 roughly. David Hilbert very much lived to see both wars though. Transformed foundation of mathematics through Hilbert's problems at the turn of the century at the time, which was 1900, and axiomatic geometry. Unified algebra, number theory, and invariant theory. With abstractions, yes, which of course, because we're humans and that's how we think, and logical formalism. He advanced the study of integral equations in what would later be called Hilbert spaces. I believe it was Neumann who coined the actual term of Hilbert spaces, but yes, Hilbert spaces are built here. Can't remember what Hilbert called them. Be interesting. Foundational to functional analysis, so yes. And he engaged with mathematical physics. This is part of that, that Einstein quote, which I brought up earlier, which is that, mathematicians took my thing and then they made it incomprehensible. Well, that's because David Hilbert here, well, one of the reasons is like he axiomatized, or at least insofar as he tried to axiomatize. I mean, if you create like a system, even if it's not like fully comprehensive, it's still a system. So it's like fully comprehensive of the entire structure with which it is trying to, of which it is trying to axiomatize. Then yes, it is, though not in its entirety, captures relativity. I don't know, does it? I'm not well versed in it enough to say for sure. Axiomatize relativity and quantum theory. Probably not though. Because that's still going. Not the relativity part per se, but there's the consequences in the quantum theory. It's mostly, yeah, okay. Emmy Noether, from 1882 to 1935. She had to leave her home because, German anti-Semitism and all that. And anti-Slavian. Just like anti-anybody that's not like, that doesn't benefit us. It's just the way it is for them. She revolutionized abstract algebra via ideals, chain conditions, structural methods, and structural methods. Okay, so in Noether's theorem, that linked symmetry. This is the thing which the physicists like a lot, I think. From what I've heard, they like this one. And conservation laws. Which is core to modern physics. She trained a generation of algebraists influencing ring theory, representation theory, and topology. Henri Lebec, Lebesgue. No, Lebec, 1875 to 1941. Reconstructed integration theory using measure theory. He developed the Lebesgue integral, Lebesgue. Which is key to probability, real analysis, functional spaces. Feared over abstraction, but he feared over abstraction insofar as it's like, look, if we keep on developing math to be more and more general, it's going to be meaningless, and it's going to be essentially meaningless in function, and it's going to be less relevant, which was his fear. She hasn't. So it's like there's this clear line in between like practice and theory, right? Like engineering and sciences, it hasn't irrelevanted itself out of existence. So, Also, it's kind of interesting because it's like, in a sense, aren't you kind of contributing that to Lebesgue? Like, aren't you anchoring rigor across these different disciplines via abstraction? But, Hausdorff, Felix Hausdorff, 1868 to 1942. Founded point set topology. I wonder what that consists of. Maybe points and sets. Point sets topology formalizing continuity, compactness, and separation axioms. Ooh, right. Just a lot more axioms because sets. He introduced the modern concept of topological spaces, and for Hausdorff, axioms. So just part of any undergraduate topology course are these axioms. His Grundzüge der Mengenlehre, 1914, remains foundational to modern topology. And he's one of the giants of the thing, you know, it's John von Neumann. Freaking John von Neumann up in here being an alien. 1903 to 1957, Martian. That's what they called them. I think like a lot of people call them like a, what is it? I can't remember. It was something Martians, one of the Martians. Mathematics, there was a phrase. It was like a book. There's a book which is his daughter wrote. He's an economist. Was an economist? She may still be alive, right? Who wrote a book on him, like living under a Martian. I think it was like it was roughly how the title was. Game theory. He developed. He was the architect of game theory, quantum logic, and modern computer architecture. He defined and axiomatized Hilbert spaces. Which are vital for quantum mechanics and functional analysis. He contributed to logic, set theory, economics, and the foundations of computing. So there's a strong argument to be made that he's actually, you know, the last sort of Eulerian mathematician who just kind of has all these things in a row. Well, not Eulerian, I guess kind of, Euler was his own thing. Eulerian, there we go. I made a mistake. Oh no. Okay, Alan Turing. Everybody knows Alan Turing now because of that movie where he's played by Benedict Cumberbatch. So Cumberbatch, because he's British, right? So it's not like he's Bach. No. Okay, so he originated the concept of the Turing machine. Computability theory was also a thing that he came up with. Computability theory. At least in its modern form, and underneath, like, you know, a banner that you could actually say, oh, that's computability theory. Well, there you go. Proved undecidability. Of the decision problem, which is like this long German word, which is a lot of German, which is Entscheidungsproblem. Oh, not actually that long. Okay, never mind. Just complaining for nothing. Which is kind of like, you know, is there a standardizable? Well, I mean, there's a lot to be said with that. So I'll just say it. Proof of undecidability of the decision problem, and I can, you know, leave the viewer to sort of look into that if they want to, and not put too much time into it here. It's a careful thing with historical mathematics. It's like, how much time do I have, which is finite, and what can I say without delving too far into theory? You know, this is already getting pretty far. Nicholas Bourbaki. He's not a real person, man. He's a group. He's a group of people. It's a little mathematical oligarchy, which is like very interesting. 1930s to 1980s. So I'm just going to refer to him as he because I know it's a group, but it's just easier if I just say Nicholas Bourbaki did this, Nicholas Bourbaki did that. So Nicholas Bourbaki rewrote mathematics from the ground up using axiomatic and structural formalism. From algebra to topology, from topology to analysis. Yeah, and that's done in a specific book, Elements des Mathématiques. Unified algebra, topology, and analysis under set theoretic frameworks and category theory as well. Also, and category theory. Because, I mean, very minimal, because category theory sort of came about, well, it came about towards the latter end of the Bourbaki group's real period of mathematical dominance. Okay. Last but certainly not least, not to be curt with you, but Kurt Gödel. 1906 to 1978. So he proved the incompleteness theorems. Which showed that no consistent system of arithmetic can be both complete and provably consistent. There's always going to be sort of an axiom that you have to sort of grind at, and really think about upon which you can base your reasoning. Incompleteness theorem. He shattered Hilbert's formalist program because of that, because of these sort of things, and then he initiated meta-mathematics and undecidability as formal constructs. His results form the boundary of what mathematics can know really about itself, what it can say about itself, because mathematics is not, of course, a totalizing epistemological framework. It's grounded in consistency, things like logic and whatnot, which are part of a bigger structure within philosophy. So, tis what it is, man. And that's what it is. At least so far as we can see for now. Pythagoras was wrong. I mean, no, he can still be right, because he just said numbers, right? So he just said numbers was everything, which is, it's a different thing than saying mathematics is everything. So, the historical overview of the 20th century can be roughly stated as follows. Let's see here. The 20th century, it didn't give us closure, it gave us recursion. Poincaré framed mathematics as intuition guided by rigor. Hilbert demanded rigor become its own intuition. Noether turned structure into language. Gödel proved that language cannot contain itself. The century was not about finding answers. It was about discovering the boundaries of what answers are, which is sort of an answer in and of itself, but nevertheless, topology ceased being shaped entirely and became more structural. Algebra ceased being computation and became more syntactical. Logic ceased being certainty and became a limit. and became more marked by a boundary of what it could do. Computation ceased being tool and became more definition. Mathematics fractured, then fused what had been separate domains, geometry, algebra, analysis, logic, physics, began to speak to each other in a common tongue of abstraction. Theorems became categories, right? And equations became functors, proof became architecture. But this unification came with a paradox. The more mathematics generalized, the more it revealed the impossibility of completing itself. Hilbert dreamed of a system that could capture all truths, right, in a logical positivist kind of way, which is overthrown because you have to have axioms, right? And those things have to be believed in, accepted, you know. Gödel proved no such system could exist. Turing showed there is no universal machine of judgment, yet with the undecidability problem, yet mathematics endured not by resolving these limits, no, but by incorporating them into its nature, what it can say, what it can't say, in regards to the underlying universe or overlaying universe. And so, universe of things. And so, mathematics in the 20th century became not merely a discipline, but a mirror. To study its truths was to confront our finitude. To extend its form was to trace the architecture of thought itself. No longer the language of certainty, mathematics became more so the discipline of disciplined uncertainty in a more unified form. And with that, we go to, finally, we get into finally the most recent trends in chapter 24. And this is from circa 1970 to the present day. Roughly, post-Hilbertian collapse, computational ascendancy, global diffusion, and figures like Kenneth Happel, Wolfgang Haken, Gorenstein, Wiles, Parolin, Walter, Yao, exist in these decades. The final decades of the 20th century were not a climax, they were a rupture. Mathematics became a battlefield of paradox, proofs indivisible to humans, groups classified by collective will, a childhood riddle undone by elliptic curves. Geometry once dethroned returned not with compass and straight edge, but with Ricci flow and software verifiers. What had once required shock now demanded machines. What had once required insight now required infrastructure. Yet at the same time, this flame, this passion of wanting to understand things mathematically endured. Problems declared too vast to finish were finished. Conjectures mocked for their absurd longevity. Fermats, Poincaré's fell not by solitary leaps, but by centuries of accumulated arc. This was the age when proof and computation crossed paths and questioned each other. Mathematical legitimacy no longer depended solely on elegance, but on code, consensus, and complexity. Nations once peripheral became centers of excellence, formalism and reality not as theory, but as architecture. The question was no longer, can this be solved? It was, can we all agree what solving even means? This was not the era of axioms per se, though of course, every era kind of is, but it was the era of verification. Not the age of founding principles necessarily, but of closing epics. How do we close onto our solution? And yet, beneath it all, doubt remained, disciplined, focused. Mathematics continued not because it was all knowable, but because rigor remained a habitually sacred thing. So, and we'll see that with these interesting things. So two things. Whoa, really? 3 things actually. Well, we'll get into 2 things for now. Four-color theorem, Poincaré's conjecture, Fermat's last theorem. Okay, so on the four-color theorem, the statement is basically thus. Any map drawn on a flat surface or sphere divided into contiguous regions can be colored using no more than 4 colors so that no 2 regions sharing a boundary segment receive the same color. So if you have like red, green, blue, yellow, you know, you can see where I'm getting at there. And then you apply that to a map. Or precisely, if each region of the map is represented by a node, and shared borders are represented by connections, then no more than 4 colors are ever needed to color all nodes, so that connected nodes differ in color. This would lead to the first computer-assisted proof. A modern computer, at least from what we know. Performed by Appel and Haken. Be funny if his name was pronounced Hacken instead, because then it's like computers and hacking. It's the 90s, so we're cool and stuff. No, it's not the 90s, it's the 1970s here. This was done in 1976. Computer-assisted proof in 1976. And so what it did is it made a crap ton of configurations, basically. A ton of configurations. I think like it's like, let me see if I have the number in my notes. Yes, introduced a method to reduce all cases to a finite set of 1,936 configurations, then showed no counterexample could contain any of them. It introduced a method to reduce all cases. And this would later, so then in the 90s, where you have like image comics and stuff, this stuff is happening, which is wild to think about. Monica Lewinsky and like all of that stuff, and then, you know, 90s stuff. Robertson, Sanders, Seymour, Thomas. These are last names, of course. They introduced a more simplified version of this, which was down to 633 configurations, discharging rules to 32. It improved algorithmic transparency and mitigated criticism of the Apple Hackett approach, because it's like, oh, can we prove things by redundancy? In which case, like, you know, it's like our group did this computer-based proof, another group did this computer-based proof, and they all got the same thing. So can we say, you know? But there's a lot behind compiler trust and hardware fallibility that raises early questions for the software verification ethics of the whole thing. Oh, and there's another one. There's another one in 2005, sorry. 2005, Gontier and Werner They actually did this with Microsoft, I think it was. Let me see. It was with a proof assistant and with machine verified certificate of correctness. It marked a shift from proof as rhetoric to proof as code artifact, which is just so wild. I mean, but this is the time we're living in, you know. Yeah, this was Microsoft program, I think was, so, no, it was Microsoft, but I can't remember exactly the terminology that we used for it. It was a program. It was Microsoft, so. So that's all we're going to say about that for now. And as you can see, like, this isn't just like, you know, one person going out there and just like coming up with a whole bunch of stuff. It's like at the very least 2, like we saw earlier, and then 4. It's like these groups of people. This is becoming more of a commonplace thing into the modern day. Just like these groups of people going about and solving things, which can be seen in like the case of finite simple groups, classification of finite simple groups. Which I'm not going to go into like full detail here, but basically it's a periodic table of finite simple groups. It was like 10,000 pages long. 10,000 pages long in the Oshbacher, because they headed it. That's the only reason like it's called Oshbacher-Smith, is because it's not just 2 people working on this, it's like a ton of people. And it was completed in 2004. So it's like computers, tons of people. It's like it's just manpower and machine being put into the grinder of mathematical rigor in order to solve things, you know. It's like, it's more of a, yeah, so. What else can be said? How about this, on Fermat's last theorem, Wiles, 1995, he proved the semi-stable case of the Tajama-Shimura-Veil conjecture, which implied Fermat's last theorem. This hadn't really been a lifelong goal for him. It was a childhood dream, but he was like, you know, it's just it's not like something where it's like, I'm going to do this, I'm going to do this. But he saw that it was possible. Once he saw that all he had to do was prove all he had to do. It was a big deal. The TSW conjecture to prove, to help imply and then prove Fermat's last theorem. He employed tools from different sections of mathematics, from Iwasawa theory, Heck algebras, Galois representations in modular forms, joint supplement with Richard Taylor, yes, resolve the critical gap in the original argument, because people criticized it and he was like, oh no, but I'll go back and fix that, but he did. So, very nice. And then, last but not least, Poincaré's conjecture. Which is simply, you know, like every closed, simply connected 3-dimensional space without boundary is topologically equivalent to a 3-dimensional sphere. So, it's like you can kind of see why I'm kind of like hiding a lot of the theory right in this lecture series, because it's not about that. It's about like the developments. It's about the developments, and this is part of the development, but you know, it's not all about the in-depth theory of the thing. So, and this is an interesting story, because it takes place from 2002 to 2003. And basically there's this Perelman, he's this really He's more on the Newton scale of things in regards to personality. So he's very isolated, he's very solitary, he's very reclusive. And he published 3 papers that outlined a proof on Arc-X. It's a proof of the geometrization conjecture, implying the Poincare conjecture. He introduced entropy formulas, surgery techniques, and refined Hamilton's Ricci flow. Verified independently by several groups, Perelman refused publication prizes and interviews, and there was like even a controversy in between whether or not him or Yao, who I mentioned earlier, Ch12, Yao, I believe, actually came up with the proof. It changed the discourse on authorship, proof sufficiency, and mathematical ethics. And that's where we leave it. That's as close to history, as close to the present day as history goes. Insofar as I could say and have it mean anything really substantial, because this is so close. 2004, 2003, that's within my lifetime. So, at the end of this lecture series then, I'll leave off with this. This was not a century of discovery per se yet. It was a century of convergence. Proof and machine become indistinguishable. Rigor no longer lived on chalkboards, it pulsed through servers. Mathematics shed its romantic loneliness and clothed itself in code, collaboration, and controversy. The four-color theorem no longer belonged to vision, it belonged to computation. Fermat's last theorem no longer belonged to arithmetic, it belonged to modularity. The Poincare conjecture no longer belonged just to topology, it belonged to flow, entropy, and aesthetic refusal. Sarah forced reckoning what is a proof if it cannot be read, what is credit if it cannot be assigned to one singular individual, that is, what is truth if it must be compiled. Mathematics hasn't answered these questions. It's endured them. Perelman, Wiles, Grantier, and Gorenstein each revealed a facet of what the discipline had become, a mirror of the world it once stood apart from, a discipline that no longer claims certainty, but never surrenders rigor. This was not an epilogue to the history of mathematics. It's a reforging into the present day in silicon, in silence, in solidarity. Thank you.